Today we are going to talk about the magnetism. What is the magnet? A magnet is any material that attracts iron or materials containing iron. So we know that this is here, you know that this is the magnets. Here, as you see in this slides, this is here, the magnets. It's attract an iron or any material contains an iron. What are the properties of the magnets? First one, all magnets have two poles. It has north and south. So any magnet in our life here must have two poles. And the magnets exert forces on each other, which we call it magnetical forces. In each part, I mean like here, if you have the magnets here, the magnets must have south and north. On the north here, it has a force, and in the south, it has a force. Some of the magnets come like straight line, and some of them will come like U-curve. It has a south here and north. And in each part, we have a force. And the magnets are surrounded by a magnetic field. And also here, and if you look at this part here, we have a magnetic field. They are strong at this part, and they will be weak at this part here. So the magnetic poles, the properties of them, they must have two poles, south and north. They must have, they have a magnetic force on each side, and they have a magnetic field on their parts. These are the properties of them. Now, the first one, or the first property, that's all the magnets have two poles. Where are the poles? The poles will be on the end of the magnet. Here, as you see, this is the first type of magnet. The poles will be on the end of the magnet. So if you have here this magnet, at the ends, we have the magnetic pole, south and north. If you have comments like here, like the U, here we have at the ends, we have the north and we have the south. We have the, south. So each end of the magnets, we call it magnetic pole. The end of the magnets is magnetic pole. And each magnet, it must have two poles. On the end of the magnet, always end up with pointing to the north. Here, if you have letter N, this letter N is point to the north, or we call it the North Pole. And the other one, the letter S, it's mean point to south or South Pole. So each magnet, it must have two parts or two poles. The poles will be at the end of the magnet. South, S, it's mean South Pole, and N, it's mean North Pole. Now, and they must be in pairs. What does it mean? That means the north part cannot become only, and you cannot see a magnet with north part only, or with south part only. They must come in pairs. And the charge, we say that we have positive charge. It can't come as a positive. And we can say that we have negative charge. So they can come have positive only or negative only. But on the magnetic, no. The two poles must come in pair, must come with each other, south and north. Even that, if you cut it, you must have south and north. So each magnet, it must have two pairs of poles. They must come in pair, one north and one south. Not north and north or south and south, one north and one south. And if a magnet is broke in half, each half gains a new pole, like here. If you have it now, this is here a magnet. It has north and south. If you cut it, one of say, teacher, if I cut it, I can have north only. No, if you cut it, there's a part here. It comes south, and at the other part, and at the other part of the cut, we have north. So even with the magnet is cut in two half, we have a new magnets, one with north and one with south, and one with north and one with south. That's why here, this is an evidence that the magnet cannot become in one south or one north. It must come in one pair. Now, so for the first property, do you have any question?
No, teacher.
Yeah, here we say that we have three properties. The first one, that all the magnets have two poles. The second one, that the magnets exert forces on each other. And the third one, that the magnets are surrounded by a magnetic field. We explained the first one, that all the magnets must have two poles. We said that the poles will be at the end of the magnet. We have S and N. S means south pole and mean north pole. And they must come in pair. Even you cut it into two halves, you must have a new pole. One is north and one is south. Now the second property, that the magnets exert forces on each other. If you bring now two magnets here, if you have two magnets, one you bring it here, and the second one you bring it here. Did you remember now in charge, we said that in charge, if we have two negative, they repel, and if you have one negative and one positive, they attract because they are different. In magnetic here, we don't we have the same, like pole attract and different pole will be, like pole will repel and different pole will attract. So if you bring here like two magnets, here we have south and north, south and north. If you bring them like this now, at this part here, the two magnets exert a force. And this one, this type of force here, we have an attractive force. From where do we have this force? The magnetic force results from the electric charge in the magnets. And since we have inside each magnet, we have an electric charge. And the electric charge will be at the end of the magnet. So if we have different, they attract. But if you have, or if you bring them like the same, such as you have this one and the other one. Here we have south and north, north and south. And where they are connected, they are connected in this point here. We have north and north. Since we have north and north, the magnets will be repel. So they comes like this. So if we have them at the connected points here, north and south, they are attracted. And if they have different, like north and north, they will be repelled. So why? Because we have a magnetic force. It's like the electric force. And the magnetic force results from the electrical charge in the magnet. Is it clear?
Yes, teacher.
Okay. Now, the magnets exert forces on each other. Let's continue that. The force can either push the magnets apart or pull them together. How? Or like what? Like the magnetic forces between magnets depends on how the poles of the magnets. If we have like poles, they will repel, and if we have opposite poles, they will attract. So if we come back here, or if we draw that, here we have two magnets. Now we say that we have here south and north, south and north. Since they are different, they will attract. And they have a magnetic force. And if we have here south and north, and here we have north and south, they will repel like the electric charge. And we have a force. And the amount of the magnetic force of the attract one will be greater than of the repel one. So the magnitude of the forces depends on how the magnets line up. If we have different poles, they will attract, and if we have opposite or same poles of this, we will repel, like the electric charge. As you see here, if the spin align, the attraction occur, otherwise the magnets repel. Here we have two magnets, one is north and the second one is south, so they will attract. But the second one here, we have north and north at the connected points here, so they will repel. So here we have north and south, they will attract. Here we have north and north, they will repel. Let's see here now. How the magnetic force or how the force will be. If they are unlike, later on we will talk about it, we have a magnetic field, so the magnetic force will come like curve. But when they come like the same south and south, they come like this. They will repel. Now, in directions, if you want to draw them here, we have north and south. Since they are this difference, so we have an attractive force. South and north, we have an attractive force. But if you have north and north, there's an repulsive force, one to the right and one to the left. And if we have here south and south, they are connected at this point here, or they are facing each other. The north part will go to the left, and the second north part will go to the right. Is it clear?
Yes, teacher.
Yes, teacher.
Now here. So the magnets is similar to what? The magnet. Is it similar to what? To the weight, to the force, to the acceleration, to the speed, to the electric charge?
Force.
The magnetic force is like the magnet is similar to the electric charge. Like poles repel, and different poles attract, like the electric charge. Like charge attract, repel, and different charges attract. Why the magnet is similar to the electric charge? Because both of them exert a forces on each other and are surrounded by a field. Because the positive has a force around it and the negative has a force around it. And the same in the magnet. The south pole has a force around it and the north pole has a force around it. Now, the third part of the third property, that the magnets are surrounded by a magnetic field. Now, let's see now here, what is the shape of the magnetic field? Now, we remembered before that if we have we have positive and negative, we said that they attract to each other like this. And they comes out like this. They aligning with each other, they connected each other because one is negative and one is positive. So for the electric charge, they are here connecting with each other. So now, and they have a field. And if we have here a positive charge, it has an electric field around it. And if you have a negative part, it has an electric field around it. So as the electric charge has an electric field around any of the electrical or any of the atoms, here we have the same for the magnets. For any magnets, here, we have a magnetic field. How the magnetic field will be? For the charge, we know that it comes like the sun here. It's like the lines that is surrounded by any atom. That's how the magnetic field will be for the magnet. We have a lines. The lines, they come from the north to the south. So here we have a lines. How the lines will be drawn? Will be drawn from the north to the south. From the north to the south. From the north, as you see here. From the north to the south. From the north to the south. And so that's mean, since they are from the north to the south, so that's mean the lines will go here out of the north, entering in to the south. So remember, they are from the north to the south. That's mean the lines out from the north got in the south. So how the lines will be? The line drawn must be drawn from the north pole, entering the south pole, as you see here. Entering the south, going out from the north. Now, here as you see, they told me that how the magnetic fields, these lines here, we call them magnetic fields. The magnetic fields line show me the direction of the magnetic field and the strength of them. Some of the parts, if you see like there's a magnet, that's the magnet's field here are very, we have many lines between two poles of the magnets. If we have many lines, that means this magnet is very strong. So the magnitude or the number of lines between the two poles of the magnet show me how the strength of the magnet will be. But if you have now any magnet, and we have only like only one, and some only how many, some lines, that means this magnet will be weak. And how can I make them strong, or how can I change the situation of them? Sometimes by changing the temperature, sometimes by cut it, sometimes by putting them. If you put the magnet on a very strong magnetic field, it will change his magnet field. So the magnets situation, or the strength of the magnets, will be changed according to some factors. If it's surrounded by a magnetic field, or a strong magnetic field, or if we put it at a high temperature, the magnet will be changed. So let's come back here. Each of the magnets must have a pull, must have a force around it, and must be in the magnet field. How can we draw the magnetic field? By lines. The lines come from the north, entering the south, so they are going out from the north, entering the south. The number of the lines show me two things. The number of the lines show me two things. The number of them show me the strength of the magnet, and the direction of the lines show me where's the north and where's the south. So here, as I told you, the closer together the lines, that means they are stronger. When we see that the lines are closer to each other, when I see that the number of the lines are greater, that means we have a strong magnetic force. Right. Now, let's see here how we have, if we have now opposite attracts. Field lines that curve toward each other show attraction. Here now, if we have north and south, okay, let's see now here how the curves will be. They comes from north to south, from north to south. So if we have here in the same magnet, we have a magnetic field coming from the north, entering the south, as we said before. And even though between two magnets we have a magnetic field, they come from the north, entering the south, from the north, entering the south, they comes like a curve. And since here the lines are connecting or are closer to each other, that means here we have a greater electrical force, a magnetical force. So here, since they are closer, so we have a greater magnetic force. So if they are attract, as you see in this part here, they comes like a curve, going from the north to the south, entering the south, out from the north. How if we have, if we put now north with north, how the magnetic field will be? If we have, as you see here, just a second, please. So as you see here, if we have two parts, they are different, two poles that they are different, there's a curve that comes toward each other. They comes like them here, they comes like a curve toward each other. But if they are repelled, they comes like a curve, but away from each other. Since they are away, that means they make a repulsion. So here, let's draw now the three cases. If we have south and north, if we have south and south, and if you have north and north. For the first one, I told you that they comes like a curve, come toward each other from the north to the south, from the north to the south. By the way, they are not straight lines, they are a curve. So they entering the sun out from the north. Now, how if we have now south and south? They comes like a curve, but they are going towards each other. Yani when the curve come, and remember, they are entering the south. So when the curve come, they didn't come from south to south. They are coming like this. Curves toward each other. So here, as you see here, in this part here, they are the dent, or they cannot now connecting them. There's a space here because they are coming like a curve, and this curve they are going out apart or going far from each other. If you have here now north and north, the north, they are going from the north, so they're coming like this. This is here how it will be for the same poles and how they will be for the different poles. Are they clear?
Yes, teacher.
Okay.
Yes.
Now, how will it be for the horseshoe magnet? This one here, I told you that we have two types. One is straight and one like Q curve. Or we can name it with horseshoe. Here, how they will be. The same, they're coming like a curve from the north to south, from the north to south, entering the south, going out from the north. So the field lines, oh here, this picture here shows me how the graph of how the magnetic lines will be on the horseshoe magnet. Now, is there a magnet in our Earth? Yes, we have. All of us know that we have geographical poles. One is south and one is north. From where they bring these geographical poles? From the magnets inside the Earth. The Earth behaves as if it has a bar magnet running through its center. Why? As there's not an magnets exactly like there's a big magnet inside the Earth. No, there's an iron and there's a nickel on the outer force that's make a magnet. So the amount of iron, the amount of nickel on the Earth make it have a magnet inside it. And they make it the poles. These poles are imaginary, and as we don't have an Exactly. They don't have a south pole and north pole on the earth. They are imaginary. They are located near to the south or geographic south pole and geographic north pole of the earth. Right. Why? Oh, what is the benefit of having a magnetic parts here? The magnetic parts protect us from the charged particles emitted by the sun. The sun. So here, imagine that we have particles coming from the sun. If the particles now come to the earth from the sun, I can enter the earth, so it's make a problem. But since the earth here is surrounded by a magnetic field, this magnetic field protects us from these particles. So it makes like a shield. This shield protects the earth from the particles that comes from the sun. Now let's talk about the magnets in motion. Now, some of you, the teacher, how can they know how the magnetic lines will be? How can they know how they comes like curves towards or curve towards N or curves N, sorry. They bring an iron fillings. These are an iron fillings. They are like if you cut the iron into small, very tiny parts. They bring them in around the magnets. They see that then the magnetic or the irons attract to the poles of the magnets. And as you see here, they makes like a curve. They told me about the shape of the lines. They comes like a curve from the north to the south and out from the north in the south. So how they know how the shape of the magnetic field? They bring an iron fillings to tell us how the magnetic lines will be. Now, as I told you at the beginning of the lesson, that since we have a magnetism, the magnetism come now. The magnetism come from the just a second, please. You know, the magnetism comes from the electric charge. If we have an electrons in the magnetism, how they will be generated. They are moving in the magnet, have an electric or north pole and south pole. And the atoms group together in tiny areas called domains. Here we have come in domains. The atoms group so comes in tiny areas, we call it domains, and each domain is like a tiny magnet. So each atom, it makes domain, it has a north and south. For them, they make a tiny magnets. We call it domain. Now, all of us know that if we bring the magnet and we put it inside a copper or beside a copper or beside an aluminium, the domain, they cancel, or the atoms of the copper here, they are north and south like this, they cancel each other. Because why? Because they are randomly oriented. But if you put them beside an iron or nickel or coupled, we have they are can say arranged in a and not randomly. They are arranged. So since they are arranged, they make a domain that's make a magnetic field. That's why if you put a magnet inside an iron, it will attract. If you put a magnets on the nickel, it will attract. But if you put it beside aluminium, they will not attract. Why? Because the poles of the atoms of the aluminium, when they arranged, they arranged randomly, as you see here. Since they are arranged randomly, so they cancel each other. So they didn't make a magnetic field. But for the iron, when they arrange in an arrangement part. When they are arranged, they make a domain that they didn't cancel each other, so they make a magnetic field. Is it clear?
Yes, teacher.
Yes, teacher.
So all the magnets have two poles, north and south. They make the repel, the opposite, they attract. They are surrounded by a field. Now, what's make the objects we have a great or a high amount of magnetics, the domain. How the domains are arranged. If they are lined up, they make a magnetic force. If they are randomly oriented, there's no magnetic force. Here, as you see, for the unmagnetic steel, they are arranged randomly, so there's no magnetic force. But for the iron, as an example in the second part, they arranged in lines, so there's a magnetic